Hello there, Mr. Sutton here, bringing you the Algebra 2 11.1 lesson on defining and using sequences in series. This will be a two-parter. In part 1, we'll be writing out terms of sequences and learning how to write rules for sequences. In part 2, we will shift our attention to finding and writing sums of series. Since we're doing a unit that's literally called sequences in series, we should probably define those words. Sequence is the one that we'll do first. There's actually two working definitions that we've got for you for sequence. One is you could think of a sequence as an ordered list of numbers. And this list could either end or it could just keep going on forever. It could be finite or infinite. So as an example, here's a list. 2, 4, 6, 8. You can probably figure out what the next number is. Now this little ... here, if you see that, that means it's an infinite sequence and just keeps going. If it were finite, then you would just see a final number with no ... after it. So this is one way of thinking of a sequence, a list. Another way of thinking of a sequence is as a type of function. Specifically, it is a discrete, which is to say non-continuous type of function. And if you were to graph one of these, you would actually not see a smooth, unbroken curve like a line or a parabola. It might have a linear pattern, but what you would actually see would just be a few points, not a line connecting all of them. And the reason for this discrete, broken up nature is because of the domain of these functions. The domain is not all real numbers. It's actually just the whole numbers, which is to say 0, 1, 2, 3, 4, 5, those sorts of numbers, non-negative integers. Because we're only allowed to plug in these specific types of numbers and get whatever output we get back from that, we only end up with single points, not a smooth, unbroken curve as the graph. Now the range of a sequence is just going to be the terms, or you could also call them the elements that you see in the sequence, whatever that sequence is. So we have a notation for the sequence, specifically for talking about certain terms of the sequence. This little a sub n, you might see this, maybe with a number instead of n. That's basically notation for the nth term. This is a way of talking about whichever term you want here. Or if you see a sub n in general, they might be talking about any term of the sequence. But you can be specific. So for example, if we saw a sub 3 for this sequence up here, that would be referring to the third term, which 1, 2, 3, that's the 6 that we see right here. Now the n here has a special name other than that little subscript. It's actually called the index of the term. It's basically which term number is it in the sequence. And although we're talking about which term number is it, I mean the first index you might think it always has to be 1. It actually could be 0 or 1. It's okay to have term number 0, and there's some people who like doing it that way. The default though, if you don't see it spelled out for you, is you can assume that the first index is 1. You can think of this as term number 1 here. Now, there are good reasons for using a 1, and there might be also good reasons for using a 0. It often comes down to doing this next thing, which is expressing the sequence in a different way other than just as a list, because this is kind of bulky. You can also express a sequence as a rule. And this rule basically talks about what you have to do to the index of each term to get the term itself. So if I start with the indices, that's plural of index, the indices 1, 2, 3, and 4, what do I have to do to 1, 2, 3, and 4 to get the terms 2, 4, 6, and 8? So one way you can express this is by writing a sub n equals whatever your rule is. In this case, we have to double all of my indices to get the actual terms. This is one way of expressing a rule. You could also write it in traditional function notation. We could say f of n equals 2n, and that would be another way of expressing this. Speaking of rules, that kind of segues into our first example here. So we're being given two rules for two different functions. We've got a sub n equals 2n plus 5, and f of n equals negative 3 to the n minus 1. And they're basically asking us to write the first 6 terms of each of these sequences. Okay, so how do we go about doing this? Well, these rules are telling you what you have to do to each index to get the term in the sequence. So we basically just have to take the first 6 indices, 1, 2, 3, 4, 5, and 6, and plug each index into whatever the rule is. So for example, if we wanted a sub 1, the first term of this, we would have to do, let's pretend that f of n is this 2n plus 5. We would have to do f of 1, plug 1 into this rule up here. Now, when you're doing this, I mean, this isn't too difficult to do without a calculator, but if you're allowed to use a scientific calculator like Desmos, it would probably be a lot faster just to define and use a function for this for these first 6 terms, because otherwise it's just a lot of number crunching. So in this case, let me show you that. So here's our good friend Desmos. Let me just move this a little bit. I'm going to just define f of n to be 2n plus 5. That was my rule up here. And now I can, just like I've been doing for all of my lessons, just do f of whatever number I want to plug in. In this case, that's 1. And again, we didn't really need a calculator for this. I mean, 2 times 1 plus 5 is 7. So, but you know, if you're doing a lot of these in rapid succession, a calculator can definitely be helpful. So 7 would be our first term. So with that in mind, pause the video and see if you can come up with the remaining 5 terms for part A, and then go ahead and do part B as well. Give it a shot. All right, let's see how this turned out. So let me just plug the rest of these into my Desmos here. So we've got f of 2 is 9, f of 3 is 11, f of 4 is 13, and you might have noticed a pattern here. I mean, we're literally just adding 2 every single time. So I think we can safely say that the 5th term is 15 and the 6th term is going to be 17. And we could keep going as long as we needed to. Let's come on over to this one now. Now this one is already in function notation, so we don't really have to spell out this f of 1 business on this one. Let me just go to Desmos and recreate this function. So let me move over here so I have room to see my answers. So now I'm just going to clear all this out, and I've got f of n equals, we'll do -3 parentheses, and I'll raise that. Now I think I'm going to need a parentheses to put n minus 1 in my exponent, otherwise the PEMDAS will get messed up. So parentheses, n minus 1, and now I can just plug in whatever I need. So if I do f of 1, that's going to be 1. And f of 2, we've got -3. And then f of 3 is going to be 9. And then f of 4, we've got -27. And you might have noticed here, you might see the pattern. It's an exponential sort of pattern. We're essentially multiplying by -3 every time. That's what this -3 to an exponent is all about. So you might be able to do the rest in your head. -27 times -3 would give us 81 for the 5th term, and -3 times that would give us -243 for term number 6, but if you want to double check it, you're always welcome to do so. For this next problem, they're asking us to write the next term, so the 5th term in this case, and write a rule for the nth term of this sequence. So we basically have to figure out the pattern and write a formula for it. And this formula should, if we're starting with an index number of 1 like I usually do, this formula should take 1, 2, 3, and 4 and turn them into these numbers here. So our thought process when we're doing this is basically, what do we need to do to 1, 2, 3, and all those numbers to get these given terms? Now, some common rules that we might encounter, we might have k times n, so these might all be multiples of some number, like multiples of 3. These could also be perfect squares or perfect cubes. Or these could all be some number raised to an increasingly higher power, different powers of a number. And just to make it a little more tricky, these might incorporate one of these common rules, plus or minus some constant. So we might be multiplying by some number and then subtracting a number. So that's the idea, that's kind of the thought process we have to go through to get this. So pause the video, see if you can figure out what the pattern is here what the fifth term should be, and then kind of write a rule in terms of n for what any term of this should be. All right, now this one is kind of tricky. If we go through kind of our common rules here, I mean, what could I do to get 1 to turn into a 2? Well, there's a few things, right? I could do 1 plus 1, so maybe plus 1 is my rule. But then if I do 2 plus 1, that doesn't give me 9, so that's not my rule. Okay, how else could I get a 2 out of a 1? Well, I could just do 2 times 1, but if I do 2 times 2, that again does not give me 9. So this is an issue. One thing you can do to try to see if there's a pattern in here that's being hidden by adding or subtracting one of these constants is you can go through these common rules and maybe write out the first few terms of what they would be and see if these numbers kind of match, if they're just shifted off by a number or two. So for example, perfect squares, 1, 4, 9, 16. Well, these numbers seem to be getting further and further away from my perfect squares, so that doesn't seem to work out. How about perfect cubes? We've got 1 and 3. 2 cubed is 8. 3 cubed is 27. That's kind of close to 28. 4 cubed is 64, which is very close to 65. So let's play this out, right? This is 1 cubed plus 1. This 9 is really 2 cubed plus 1. 28 is 3 cubed plus 1, and the same thing with 4 cubed, so I think this is our pattern. So if we want to get the fifth term, then we would have to do 5 cubed plus 1. And what would 5 cubed plus 1 be? Well, 5 cubed is 125, plus 1 is 126. So that would be our fifth term. In our rule then, we just have to replace this number that we keep changing with an n. We could say a sub n equals n cubed plus 1. So as you can see from the analysis we just did, there's not really a one-step cookie-cutter approach for doing these. You have to try a bunch of different possibilities until you find something that fits. Here are a couple more examples for you to try out your creativity. Pause the video and see if you can write a fifth term in a rule for example number 3 here. All right, let's see how we did on this one. So let's see, 1, 6, 11, 16. One thing you might notice about this if you're looking at patterns is that it looks like we're going up by a common difference of 5 each time. So if you have a common number that you keep adding over and over, that suggests that these things are multiples of something. How about multiples of 5? So 5, 10, 15, 20. These aren't exactly multiples of 5, but they're pretty close. 1, for example, is 5 times 1 minus 4. 6 is 5 times 2. It's 10 minus 4. 11 is 15 minus 4. That's 5 times 3 minus 4. So it looks like this pattern is holding so far, and it still holds for this fourth term as well. So for our next term then, we would have 5 times 5 minus 4, 25 minus 4, which would give us 21. And then in general, we can write our rule as 5n minus 4. Next up, we have this fun-filled fraction sort of problem. Now, for this one, you're going to try it on your own in just a moment. Just a little bit of a hint here, and that is you might want to consider the numerator and the denominator separately, and consider the idea that you can have one of these n's changing in more than one spot in your terms. So with that in mind, pause the video and give it a shot. All right, so I'm going to look at the numerator and denominator a little bit separately here. For the numerator, I've got 1, 3, 5, and 7. So I'm just adding 2 each time. So that suggests to me that I've got some kind of multiple of 2 sort of thing going on. So if I did 2 times 1, 2 times 2, 2 times 3, that would give me 2, 4, 6, and 8. So if I just subtract 1 from that, I ought to be able to get these. So I've got 2 times 1 minus 1, giving me this first one. And now for the denominators, let's just look at those. I mean, 10, 20, 30, 40. That's pretty straightforward. It's just 10 times 1, 2, and 4, or 3 and 4. So we've got 10 times 1 there. For the next one, is this going to be 2 times 2 over 2 times 2 minus 1 over 10 times 2? Well, this would be 3 over 20, which matches what I have there. Next up, I should have 2 times 3 minus 1 over 10 times 3. And that's going to be 5 over 30, unreduced. So there it is. So it looks like this is what we're looking for. So for my fifth term then, I need 2 times 5 minus 1 over 10 times 5. That's going to be 10 minus 1, so 9 over 50. And then in general, I've got 2 times n minus 1 over 10n. For this problem, we have a big old pile of apples at a grocery store, and you're stacking these apples in the shape of a square pyramid with 7 layers. That's pretty elaborate. We want to write a rule for the number of apples in each layer, and then graph that sequence. So I'm going to have you pause the video and figure out the rule part on your own, and then we'll graph that together and I'll show you how you could do this on Desmos. So pause the video and give it a shot. Alright, so let's just build our way up here. So for layer 1, that's the top here, I just have 1, which I could say 1 squared is 1. The reason I have the squared there is I'm going to need it for the rest of these because it's literally a square pyramid, so each layer is a square with the same 2 sides going in each direction. So for layer 2, we've got 2 squared, which is going to be 1, 2, 3, and that fourth apple we can't see. For layer 3, now we've got 3 apples on each edge of the square, so that's 3 squared for a total of 9 apples. And we could keep going. The seventh layer, of course, will have 7 squared, 49 apples down there. You don't have to count them, though. Our general rule then is going to be n squared, f of n equals n squared. Now, in order to graph this out on Desmos or anywhere else, it's a little bit tricky here. You have to be mindful of the fact that this is not a continuous function. This is a discrete function. So if I were to just go into Desmos and graph f of n equals n squared, let me actually just do that. So here we go. F of, can I use n? Let me think. Nope, it wants a slider there. Let me use x. So f of x equals x squared, and predictably it gives me a parabola, but this isn't the graph of the sequence function, right? Because there is no layer 2.5 or whatever else is in between these. So to do this, we're instead going to use a table. So I'm going to do the little plus and do a table, and the benefit of using a table is I can get individual points. So for my x's, I'm just going to do 1, 2, and I can auto-complete that all the way to 7, or as far as I want to go. Now for the y1, I could put in all of these squares if I wanted to. If you don't feel like going to all that work, another thing you can do to instantly do all of them at once is you can replace the y1 in your Desmos table with an x1 rule. And the rule in this case would be x1 squared. So let me go ahead and do that. So I'm going to delete the y1, and if you want, you can copy and paste the x1, or if you want to get the little 1 down there, you can do x followed by an underscore, so underscore, and that gives you the ability to put a base on that. And now let me raise that to a power, so exponent, and then second power. And then instantly I've got all my perfect squares. One other little finishing touch is let's just get a zoom fit to get all of those in one place, and there's our nice little graph of the number of apples at each layer. And here's a copy and paste of what all that looked like. So this concludes part 1 of our lesson on using and defining sequences in series. So pause the video, go have an apple, do some of those practice problems on sequences, and then come back and we will take a look at series. Welcome back for part 2 in this lesson. In this one, as mentioned, we're going to be taking a look at what a series is and how to work with those. So let's define this. Now remember that a sequence is an ordered list of numbers. A series is just the sum of a sequence. So for example, in part 1 we saw the sequence 2, 4, 6, 8. The series that goes with that would be 2 plus 4 plus 6 plus 8. Now this is one way of writing a series. This is called the expanded form, and it doesn't look too bulky right now, but you can imagine if you had a series with, say, like 400 terms in it, that would be kind of a pain to write. So there's actually a shorthand way of writing this called summation or sigma form. And the reason it's called sigma form is because it's based off of this letter sigma from the Greek alphabet. It looks like a big E. It's actually the Greek S, if you believe it. So here is the summation form of what we've written over here. So we would pronounce this the summation or sum of 2I from I equals 1 to 4. So let's take a look at all the little bits and pieces of this. I mean, we know this Greek symbol at this point, but let's break this down and say what each of these parts is actually doing to give us this expanded form. So this 2I here, this is called the summand. Kind of like a radical has a radicand inside it, the summation has a summand. This is the rule that we're actually going to be applying to each of these index numbers. So whatever I'm plugging in, I'm going to plug it into 2I here. Now, what am I actually plugging in here? Well, that's what these bottom and top numbers are. The 4 up here is called the upper limit of summation, and the 1 down here is, well, shocker, the lower limit of summation. Now, what do these actually do? The lower and upper limits of summation are basically the starting and ending index numbers that you're going to be plugging into your summand. So this is saying, okay, we're going to start with 1, and then counting by ones up until we get to 4, we're going to plug all those numbers into the I here. So we can plug in 1, 2, 3, and 4. Now, it is worth noting that you don't have to start at 1. You could start at 0 or any whole number, and that's fine. But here we're starting with 1. And it's also worth noting that what if your series is infinite? What if I had a plus dot 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 on the end of this so that there is no highest number? Well, if I have an infinite series, I can have an upper limit of infinity. I would just put infinity up here, and that would be totally okay. All right, now there is one more little piece that we have to mention, and that's this letter here, this little I. That is actually called the index of summation. This is the summand variable. It's telling us what to plug the numbers in for. So the expression that we have here, because this is an I down here, this is saying, okay, we've got 2 times 1, 2 times 2, 2 times 3, 2 times 4. We're going to plug 1, 2, 3, 4 into the I specifically. Now this is just worth noting, and we always have to write this letter here, because if there is a letter here that's different than the letter in the summand, we don't plug into non-index letters. So for example, if I had the expression summation of I equals 1 to 4 of 2n, because there's no I in here, I don't actually plug the 1, 2, 3, 4 into anything. It's like kind of having an invisible 0 times I going on. So this would actually be just 2n plus 2n plus 2n plus 2n. That would be the first, second, third, and fourth terms, because there's nowhere to plug this I in. So this is what this thing would actually evaluate to. And I could simplify this, but since I don't know anything else about n, I just kind of would have to leave it that way. So that's an important detail. So now that we've gone over the ins and outs of summation notation, we're going to take each of these series that are in expanded form and convert it into summation notation. So we'll actually do the first one together just to give you a sense of how to go about doing this. So my first step is I want to write my summation symbol with the lower limit. If possible, try to use 1 for the lower limit, just because it's easier to figure out the summand formula if the first thing is a 1. Sometimes it would be easier if the first thing was a 0 that you were plugging into your formula. So I guess, case by case basis, but I try for 1. So I'm just going to write summation of something from I equals 1 to something. I got to figure out my summand and my upper limit. Now for the summand, this is just going to be the nth term rule that you already were finding in part 1. So figure out the rule that you need to plug in 1, 2, 3, 4, and all those to get 7, 10, 13, 16, and 19, and that's what's going to go here in the summand spot. So let's think about this. We've got these numbers where it looks like we're adding 3 each time. So this looks like a multiple of 3 sort of situation. So if I just write out the multiples of 3, I've got 3, 6, 9, 12, and 15. It looks like in each of those cases, my multiples of 3 are almost what I need, except they're 4 less than the numbers in my series. So if I do 3i minus or plus 4, 3i plus 4, that should give me each of these. And we can test out a few just to make sure. So 3 times 1 plus 4 is 7. 3 times 2 plus 4 is 10. 3 times 3 plus 4 is 13. And as a general rule, if you've tried out 3 of these things and it's working, you've probably got the right rule. It's very rare to go 3 into a series and still have the wrong rule. All right, let's get our upper limit of summation now. Now, this is another reason that I like to use 1 for the lower limit, because if you did use 1 for the lower limit, then the upper limit is just going to be the number of terms. If lower limit is 1, upper limit is just however many terms you have here, because you're just literally counting 1, 2, 3, 4, 5. There's 5 of these. Now, if you did not choose 1 for your lower limit, you can still work around it, but then you'll have to shift everything to accommodate the number of terms. So if you used 0 for this one, then you would have to use 4 up here, because if you count from 0 to 4, that gives you your 5 terms. If for some reason you use 2 here, then you'd want to use 6 up here. All right, so that's how to do one of these. Pause the video and see if you can figure out B and C. All right, let's give each of these a shot. So looking at B, again, I'm going to just start with 1 as kind of my default I value to begin this. If I really find it unwieldy, I can go back and change my mind, but I like to start there. Now, what formula could I use for these? So 2, 4, 8, 16, 32. Well, these are actually all powers of 2. So if I had 2 to the I, that would give me the positive version of all these. If I want to get the negative version of all these, how about if I did negative 2 to the I? Let me try out a few of these. So negative 2 to the 1 is negative 2. Negative 2 to the 2 is positive 4. So that works out. Now, if it worked out that this first term was positive, then that might be a situation where I let my I equal 0 to begin with, so that my first thing would come out positive, but then I'd have to have some other things in there to make sure 2 is my first term. Now, what should my upper limit be? Well, we've got 5 terms and I started at 1, so again, I can use 5 there. All right, let's take a look at part C. So for this one, again, let me start with 1 as my lower limit. Now for the formula, again, with fractions, I often look at the numerator and denominator separately if there's not an obvious, like multiplying, adding the same number and over again sort of pattern. So my numerators, we've got 1, 2, 3, 4. Well, those are literally just my index numbers. So if I just use I for my numerator, I'll get all of these numerators. So that's pretty easy. Now the denominator, 2, 3, 4, 5, well, that is literally just 1, 2, 3, 4 with 1 added to all of them. So I can do I plus 1 for the denominator. So I over I plus 1 would give me what I need for this. And my upper limit of summation, we got to be careful here. Although there's only 4 terms written, we see this plus dot 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 here. That again means that we have an infinite series. So that means infinity is my upper limit of summation. For the next few problems, we're going to be starting with summation notation and using that to figure out the sum. You could put this in expanded form as part of doing that, but we'll see that there's some other situations where we can shortcut the process a bit. But this is kind of your traditional, no real shortcuts sort of process. So how can we do one of these? So you're basically going to be taking all of your indices, that's again, plural of index, from your lower to your upper limit of summation, plugging them all in, and adding all of those things together. Now, you could do this by hand, and I'm sure you're capable of squaring 4 and adding 3 and all these other ones a bunch of times. But if you're allowed to use a scientific calculator, especially Desmos, why not use it, right? So I would recommend that you define and use a Desmos function for this summand and use that to calculate this summation. So pause the video and try that approach. All right, so let me go to Desmos. Here's Desmos. And let me define my function. So I'm going to call this f of, you can use whatever letter you want. I'll use f of k just to match what I have here. And I'm going to write that equals 3 plus k squared. So there's my function. And now that I've got this function, I can plug in anything I want for k. Well, I want to plug in 4 and 5 and 6 and 7 and 8. So let's let f of k equal 3 plus k squared, just so I'm telling people where this f is coming from. And then I'm going to do f of 4 plus f of 5 plus all the rest of these. This is exactly what I'm going to do on my calculator. So let me just do that. So f of 4 plus f of 5, and it's just going to do all that calculation and add it for me. I mean, I'd have to use the calculator for some of this anyway, probably, so why not just tell people what I'm using and plug it all in. So that comes out to 205. So that is the summation of this thing. Now there is a way to do this on the Desmos graphing calculator that you can just directly plug in the original expression, but you're not going to have that necessarily on a quiz. You might just have the scientific calculator, so we want to know how to do it this way just in case. For our next example, they're asking us to find the sum of the summation of k squared from k equals 1 to k equals 70. Well, that's a little excessive. So we could do this like we did the last problem. We could write, f of k equals k squared, f of 1 plus f of 2 plus f of 3, all of those all the way to f of 70. But that's going to take a while to plug all of those into even Desmos. So we're hoping there's a faster way to do it. And in fact, there are. So here are some summation shortcuts that are useful when you have ridiculously obnoxious too many indices to plug in. So there's a few of them. The first is if you have the summation from I equals 1 to n of just 1, literally the number 1. So basically all of your terms are just 1s, and you're just adding all these 1s together. Well, how many n's am I adding? How many 1s am I adding together? Well, there's n of these, right? Because we're going from 1 to n. So that means that the sum of all those will just be n, which is kind of nice to not have to add 1,000 1s together. Now another shortcut that's a little bit less intuitive where it comes from, that we're not going to prove, but I'll give it to you, is if you have the integral from I to 1 to n of just I. So this would be like 1 plus 2 plus 3 plus 4. So shortcut for that is going to be n times n plus 1, all of that over 2. And again, we're not going to prove where that comes from, but you can use it. And then there's another one I'll give you. Let's do I squared. There's one for I squared. So this would be like 1 plus 4 plus 9 plus 16. So this formula is a little more complex. We're going to have n times n plus 1 again, but we're also going to have 2n plus 1, and we're going to be dividing all of that by 6. So a little bit more going on there. A little bit of a pain to use this formula and remember it, but it's better than, having to write out 70 of these and, do all that. And it turns out, if you're wondering, yes, there are formulas like this for I cubed and I to the 4th, and I think you can keep going. They just get more and more complex. At some point we stop using these shortcut formulas and actually use the graphing calculator. But you've got this problem down here to work on. Before you work on that, though, just a few other helpful things you can do, because you might be looking at these formulas and being like, well, that's great if I see like exactly 1 or I squared, but what if there's like a 3 in here? Or what if this is like a minus 5? What could I do in those cases? Or if there's like a 3i minus 5 inside there. So we can often use these formulas if we first split up the summation over addition or subtraction, or if we take a constant out from the summand. So let me show you what I'm talking about. So if we have the summation of two different things from 1 to n, we can actually break this up into the summation of your A stuff there plus the summation of your B stuff. Same limits of integration, just totally splitting that up into two different things. And just as another example about this whole taking out a constant sort of thing, let's say that I have the summation of k times some formula here. If this k is a constant, I'm actually allowed to just take that outside the summation, do all this summing stuff first, and then just multiply that by whatever the k value was. And the intuition behind this is, let's say that I had like 3 times I could multiply 3 by all of my indices and add all that together first, or I could undistribute that 3 from everything and then just add all the i's and multiply the 3 after. So it's basically just undistributing, factoring out a common factor. With all that in mind, pause the video and see if you can quickly find the sum of what we've got down here. Alright, so this is definitely the I squared sort of formula, so we're just going to use that. So we're going to be doing our n value here, in this case is 70. It is important to verify that you've got a 1 for your lower limit, because this only works if 1 is your starting value here. So this is going to be 70 times 70 plus 1 times 2 times 70 plus 1 all over 6. So all of that stuff. And let's go to Desmos and just plug all that in. So let me do a fraction. We've got 70 plus 1, 2 times 70 plus 1, all of that over 6, and that comes out to 116,795. Again, it's sort of a bulky formula, but again, way better than taking 70 of these squared terms and adding them all together by hand. All right, we've got one more problem for you to tackle here. This one is the summation of 3n minus 5, that sounds familiar, from n equals 1 to 200. So yeah, definitely, doing this the f of 1 plus f of 2 plus f of 3 way is going to take forever and a day. So pause the video and see if you can figure out a more clever way to do this using those formulas and properties we just talked about. Alright, so one thing that would help me out here is if I split this up into 2 different summations. So let's do one for 3n and another for negative 5. So we have summation of 3n plus summation of negative 5. So this at least gets us down to kind of an I and like a 1 sort of situation. But I can't truly use those formulas from the other page unless I have just n and 1 in these summations. So my next step is I'm going to take that constant that's in my way out of the summation. So I can rewrite this first one as 3 times the summation of n. And this one I'm going to write as negative 5 times the summation of 1. Yep, I can factor a negative 5 out from 1, or from negative 5, no problem there. So now I can use my formulas. So here are 2 formulas that'll be useful again. So here's the formula for when you have summation of I, and here's the other formula. Well, actually, let's just use it, and then we'll do the other formula. So summation of I, n times n plus 1 over 2. So this here is going to be 3 times, and now this is going to be 200 times 200 plus 1 over 2. So that's this first summation using that shortcut formula. For this next one, we have summation of 1. Remember, that's just n, whatever your upper limit of summation is. So in this case, this is just going to be minus 5 times the n value here would be 200. And we could plug all this in Desmos, or maybe do it without Desmos, but let me plug it in. So we've got 3 parentheses, fraction, 200 times 200 plus 1, and then we have a 2 down there, minus, we have 5 times 200, so that all comes out to 59,300. So just to make sure that this actually works, and also just give you one shot at actually using this formula in its original form on Desmos, just for fun, check your answer here by evaluating this original summation on the Desmos grapher, and to get this sigma form, you just have to type the word sum. Pause the video and try that out. Alright, so here's my Desmos grapher, and again, you need the grapher in order to use this notation. It does not work on the scientific calculator. So let's do SUM, sum, and we've got n equals 1 to 200, And then for my summand, I'm going to do, let's see here. I don't know if I need a parentheses or not, but I'll use one. 3n minus 5. And that comes out to 59,300, just like we got here. Awesome. That's the end of that one. That was some lesson, wasn't it? Till next time, Mr. Sutton signing off.